For the analysis of AC circuits, we need to know the phasor quantities and we need to know the phasor algebra as well. During the analysis of the AC circuits, we shall represent the AC voltage and the AC current with the help of phasor quantities. So let us define a phasor quantity. Phasor quantity is a complex quantity. This complex quantity has a real component as well as an imaginary component. Phasor might be a scalar quantity, it might be a vector quantity. The nature of a phasor quantity depends upon the nature of the original quantity. If the original quantity is a scalar quantity, then the phasor for this quantity will be a scalar phasor. And if the original quantity is a vector quantity, then this phasor will be a vector phasor. In any case, phasor behaves like a vector quantity. Phasor behaves like a vector quantity. Phasor has a proper magnitude and it has a proper angle. So the angle gives you direction of the phasor. So phasor is a complex quantity, and this complex quantity has a real component as well as imaginary component. There are four ways to represent a phasor. So we are going to talk about the representation of a phasor quantity. The rectangular form of representation, we know that phasor is a complex quantity and any complex quantity has a real component as well as imaginary component. The real component is represented by A and the imaginary component is represented by B. So A represents the real component of the phasor quantity and B represents the imaginary component of the phasor quantity. In electrical engineering, iota is replaced by J, where J is under root minus 1. So this form of representation is known as rectangular form. In the rectangular form of representation, we represent the real component of the phasor quantity by A and we represent the imaginary component of the phasor quantity by B. So graphically, this is how we represent a phasor. So we represent a phasor with the help of an arrow. The length of this arrow gives you the magnitude of this phasor quantity. Let us discuss the graphical representation of a phasor quantity. So the real quantities are taken along x-axis, and this is why x-axis is known as the axis of reals. The imaginary quantities are taken along y-axis, and this is why y-axis is known as the axis of imaginaries. So here is a phasor quantity. This phasor quantity has a real component which is represented by A and it has an imaginary component which is represented by B. So you see, if we look at the previous equation, you see there are two components of a phasor quantity, the real component which is A and the imaginary component which is B. and we focus on the right hand side of this equation. So the real component of a phasor quantity behaves like a phasor. Similarly, the imaginary component of a phasor quantity behaves like a phasor, and phasors behaves like vectors. So on the right hand side, we add two phasors, and we add two phasors according to head to tail rule. So we shall add the real component and the imaginary component of this phasor quantity with the help of head to tail rule, and the addition of these two components according to head to tail rule results in this phasor quantity. So you see, we look at this diagram, the real component of this phasor quantity and the imaginary component of this phasor quantity are added in accordance with head to tail rule, and the addition of these two components in accordance with head to tail rule results in the phasor quantity. Here is the phasor Z. The length of this line will give you the magnitude of this phasor, and we consider the angle of this phasor with respect to x-axis. So we consider the angle of this phasor quantity with respect to x-axis. This is why x-axis is known as the reference axis as well, because we shall consider the angle of the phasor quantity, the angle of a phasor quantity with respect to x-axis. So we can consider this angle with respect to x-axis either in counterclockwise direction or in counterclockwise direction. So in the counterclockwise direction, this angle is theta and this angle will be positive. So if you want to consider the angle of this phasor quantity in the counterclockwise direction with respect to x-axis, then the angle of this phasor quantity will be positive. And if you want to consider the angle of this phasor quantity with respect to x-axis in the counterclockwise direction, this angle will be negative. Let us assume that this angle is alpha, so this angle will be a negative angle. So we shall consider the angle of this phasor quantity with respect to x-axis either in the clockwise direction or in the counterclockwise direction. If we consider the angle in the clockwise direction, the angle in the clockwise direction will be positive, while the angle in the counterclockwise direction will be positive, while the angle in the clockwise direction will be negative. So this is the graphical representation of a phasor quantity. So you see, a phasor quantity will have a proper magnitude. The length of this line will give you the magnitude of this phasor quantity, and it has a proper angle, and the angle of this phasor is represented by theta. So we shall represent the magnitude of the phasor quantity with the help of this angle, with the help of this symbol, and we shall represent the angle of the phasor quantity with the help of theta. So a phasor quantity will have a proper magnitude as well as a proper angle. We consider another form of representation that is known as the trigonometric form of presentation. So let us consider the real component of the phasor quantity in the previous diagram. So we consider the real component of this phasor quantity in the previous diagram. So let us go to the previous diagram and let us consider the real component of this phasor quantity. So the magnitude of the real component in this diagram will be equal to the magnitude of this phasor into cos of theta. So this is how we represent the magnitude of the real component. So the magnitude of the real component will be equal to the magnitude of z into cos of theta. Similarly, the imaginary component of this phasor quantity will be equal to the magnitude of the phasor quantity into sine of theta. So if we look at this particular diagram, the real component of this phasor quantity is represented by the real component of this phasor quantity, which is represented by A, is equal to z cos theta, and the imaginary component of this phasor quantity is z sine theta. So A is the real component of this phasor quantity, that is equal to z cos theta, and B is the imaginary component of this phasor quantity, which is z sine theta. So what we do, we put these two values in this particular equation. So we put these two values in this particular equation. If we put the value of A and the value of B in this particular equation, Z will be equal to the magnitude of Z into cos theta plus J into the magnitude of Z into sine theta. So we put the value of A and B in this particular equation, and we get Z cos theta plus J Z sine theta. And if we rearrange this equation, we obtain another equation, which is equation number 2.39. So this phasor quantity will be equal to the magnitude of this phasor quantity into cos theta plus j sine theta, and this form of representation is known as trigonometric form of representation. In the trigonometric form of representation, z represents in the trigonometric form of representation, z represents the magnitude of this phasor quantity, and theta is the angle of this phasor quantity. So this means that if we want to represent a phasor quantity with the help of trigonometric form, we need to know the magnitude of the phasor quantity as well as the angle of the phasor quantity. So the question arises how to calculate the magnitude of the phasor quantity. So for the calculation of the magnitude of the phasor quantity, we consider the graphical representation of this phasor quantity in this particular diagram. So you see, if we look at this diagram, this triangle is a right angle triangle. So the hypotenuse of this triangle is z. This will be the magnitude of the hypotenuse. The magnitude of the hypotenuse will be equal to z. The base of this triangle is A, and the perpendicular of this triangle is B. So we apply Pythagoras theorem to this right angle triangle. According to the Pythagoras theorem, the square of the hypotenuse will be equal to the square of the base plus the square of the perpendicular. So if we apply the Pythagoras theorem to this right angle triangle, we can find out the magnitude of this phasor quantity. So let us consider this equation over here, and let us find out the magnitude of the phasor quantity. So we apply Pythagoras theorem to the graphical representation of the phasor quantity in the previous diagram, and we obtained this equation. According to this equation, the square of the magnitude of the phasor quantity will be equal to square of the real component plus square of the imaginary component, and we can find out the magnitude of the phasor quantity with the help of this particular equation or from this particular equation. So the magnitude of this phasor quantity will be equal to under root square of the real component plus square of the imaginary component. So we shall use this equation to find out the magnitude of a phasor quantity. So the magnitude of a phasor quantity is equal to under root square of the real component plus square of the imaginary component. Now the question rises how to calculate the angle of the angle of the phasor quantity. So let us consider the previous diagram once again. So we consider the previous diagram, the diagram which gives you the graphical representation of a phasor quantity. If we look at, you see, this right angle triangle, here is the perpendicular of the triangle and here is the base of the triangle. So according to the trigonometry, tangent of this angle theta will be equal to perpendicular divided by base. So this equation gives you tangent of the angle theta, and from here we can find out the angle of the phasor quantity. So we consider these equations. We consider the equation for tangent theta over here. So tangent theta will be equal to the imaginary component by the real component, and from here we can find out theta. So theta will be equal to tangent inverse b by a, where b is the imaginary component of this phasor quantity and a is the real component of this phasor quantity. So this is how we represent a phasor quantity in the trigonometric form. If you guys want to represent a phasor quantity in the trigonometric form of representation, you guys need to know the magnitude of the phasor quantity and the angle of the phasor quantity. So we can compute the magnitude of the phasor quantity with the help of this particular equation. The magnitude of the phasor quantity will be equal to under root square of the real component plus square of the imaginary component, and we can find out the angle of the phasor quantity with the help of this equation. Theta will be equal to tangent inverse b by a. B is the imaginary component and a is the real component. Exponential form of representation. So exponential form of representation, we know that e raised to power j theta is equal to cos theta plus j sin theta, and e raised to power minus j theta is equal to cos theta minus j sin theta. And we consider the trigonometric form of this phasor quantity. So where is the trigonometric form? Here is the trigonometric form. You see, here is the trigonometric form of this phasor quantity. We know that this cos theta plus j sin theta is equal to e raised to power j theta, right? So this phasor quantity can be written as we have z, which is a phasor quantity, and this phasor quantity will be equal to the magnitude of z. This symbol represents the magnitude of this phasor quantity into e raised to power j theta. So this form of representation is known as exponential form of representation. Let us talk about the exponential form of representation in the proper slides. So we know that cos theta plus j sin theta is equal to e raised to power j theta, and cos theta minus j sin theta is equal to e raised to power minus j theta. And we put the value of cos theta plus j sin theta in this particular equation. Z is equal to the magnitude of z into cos of theta. Okay, let me erase this equation. So z is equal to the magnitude of z into cos of theta plus j sine of theta. So we put the value of cos theta plus j sine theta in this equation, and we obtain this particular equation for the phasor quantity. So the phasor quantity will be equal to the magnitude of the phasor quantity into e raised to power j theta, and this form of representation is known as exponential form. Once again, if you guys want to represent the phasor in exponential form, you guys need to know the magnitude of the phasor quantity, and you guys need to know the angle of the phasor quantity. So there are two important parameters of a phasor quantity, its magnitude and its angle. And you know that the magnitude of a phasor quantity is calculated with the help of under root square of the real component plus square of the imaginary component. So we can calculate the magnitude of a phasor quantity with the help of this particular equation, and we can calculate the angle of this phasor quantity with the help of tangent inverse the imaginary component by the real component. So if you guys want to represent a phasor quantity either with the help of trigonometric form or with the help of exponential form, you guys need to know the magnitude of the phasor quantity, and you guys need to know the angle of the phasor quantity. So anyhow, this form of representation is known as exponential form. So let us talk about the polar form of representation. You see, we know that there are two important parameters of a phasor quantity. That is the magnitude of a phasor quantity and the angle of a phasor quantity. If we know the magnitude and if we know the angle, we can represent this phasor in exponential form, we can represent this phasor in trigonometric form, we can calculate the real component of the phasor. We know that the real component of the phasor will be equal to the magnitude of z into cos theta, and we know that the imaginary component of this phasor quantity will be equal to the magnitude of z into sine of theta. So if we know the magnitude of this phasor quantity and the angle of this phasor quantity, we can find out the real as well as the imaginary component of this phasor quantity. So we can represent a phasor quantity in trigonometric form, exponential form, as well as the rectangular form of representation if we know the magnitude and the angle of the phasor quantity. So these are the two important parameters. Which are the two important parameters of a phasor quantity? The magnitude and the angle. So in polar form of representation, we just represent a phasor with the help of this particular equation. On the right hand side, this quantity represents the magnitude of the phasor quantity, and this quantity represent the angle of the phasor quantity. So once again, if you guys want to represent a phasor quantity in polar form, you guys need to know the magnitude of the phasor quantity, and you guys need to know the angle of the phasor quantity. So you guys need to know how to convert a phasor quantity from rectangular form into polar form. You guys can make this conversion with the help of your calculators. So it's very important to convert the rectangular form of representation to polar form and the polar form of representation into rectangular form with the help of your calculators. These two are very important form. We shall do the numerical examples of the AC circuits during the analysis of the AC circuits, and we will convert the rectangular form of representation into polar form of representation and the polar form of representation into rectangular form of representation. So we represent a phasor quantity with the help of different ways. We can represent it in rectangular form, we can represent it in trigonometric form, we can represent it in exponential form, and we can represent it in polar form. So let us discuss the addition of phasor quantities. You see, phasors behave like vectors. So the addition of two or more than two phasors will result in a new phasor quantity. And this new phasor quantity will have a proper magnitude as well as a proper angle. So there are two important parameters of a phasor quantity, the magnitude and the angle. So the addition of two or more than two phasors results in a new phasor, and this new phasor will have a proper magnitude and it will have a proper angle. So for the addition of phasors, we consider two phasors in exponential as well as polar form. So let us consider two phasors Z1 and Z2 in exponential as well as in exponential as well as polar form. So we consider a phasor Z1. Here is the exponential form of representation. Here is the magnitude of this phasor quantity, and here is the angle of this phasor quantity. So if the magnitude and the angle of this phasor quantity is known, we can represent the same phasor in polar form. This quantity gives you the magnitude of the phasor, and this quantity gives you the angle of the phasor. So we have represented Z1 in exponential as well as polar form. Let us consider another phasor Z2, and let us represent this phasor in exponential as well as polar form. So here is the magnitude of this phasor, here is the angle of this phasor. These are the two important parameters of a phasor quantity. So if the magnitude of a phasor quantity is known and the angle of a phasor quantity is known, we can easily represent this phasor quantity in polar form. This quantity represent the magnitude of the phasor, and this quantity represent the angle of the phasor. So we add these two phasors, and the addition of these two phasors results in a new phasor. Here is the resultant phasor. The resultant phasor is represented by ZA. So the resultant phasor will be equal to Z1 plus Z2. The addition of two or more than two phasors results in a new phasor quantity. So we put the value of Z1 and Z2 on the right hand side. So the resultant phasor will be equal to the magnitude of Z1 into e raised to power j theta 1 plus the magnitude of Z2 into e raised to power j raised to power j theta 2. So this will be the mathematical equation for the resultant phasor. So if this is a resultant phasor, then this resultant phasor will have a proper magnitude as well as a proper angle. So if we focus on the right hand side of the this particular equation, we don't know what is the magnitude of the resultant phasor and what is the angle of the resultant phasor. So what is the problem with the right hand side of this equation? The problem with the right hand side of this equation is that we cannot find out the magnitude of the resultant phasor and the angle of the resultant phasor from the right hand side. If you focus on the right hand side, you have the magnitude of Z1, you have the angle of Z1, you have the magnitude of Z2, you have the angle of Z2, but where is the magnitude of the resultant phasor? We don't know how to find out, you see, where is the magnitude of the resultant phasor, how to find out the magnitude of the resultant phasor, and we don't know what is the angle of the resultant phasor. So it's a bit difficult to add two or more than two phasors in exponential form, right? Why? Because this is the addition of two phasors in exponential form of representation, and the right hand side does not give you the magnitude of the resultant phasor, and it does not give you the angle of the resultant phasor. So we conclude that we cannot add two or more than two phasors if they are in exponential form. Similarly, we consider these two phasors in polar form. So let us consider these two phasors in polar form of representation. So we add these two phasors in polar form, and we know that the addition of these two phasors will result in a new phasor quantity. So here is the resultant phasor. The resultant phasor is equal to Z1 plus Z2. We put the value of Z1 and we put the value of Z2 on the right hand side. So we have the magnitude of Z1 and we have the angle of Z1, which is theta 1 plus the magnitude of Z2 and the angle of theta 2. So this is the right hand side of the resultant phasor. Now what is the problem with the right hand side of the resultant phasor? The problem with the right hand side of the resultant phasor is, here is the resultant phasor. If this is the resultant phasor, then this resultant phasor will have a proper magnitude. We cannot find out the magnitude of the resultant phasor from the right hand side. You see, we have the magnitude of Z1, we have the magnitude of Z2. Where is the magnitude of the resultant phasor? Nobody can show me the magnitude of the resultant phasor. Nobody can find out the magnitude of the resultant phasor from the right hand side of this particular equation. Similarly, this resultant phasor will have a proper angle. So what is the angle of the resultant phasor? Nobody can tell me that this is the angle of the resultant phasor. So we have the angle of Z1, we have the angle of Z2, but we don't have the angle of the resultant phasor in this particular mathematical expression. So this is the problem with the right hand side of the resultant phasor. So we conclude, if the phasors are in polar form, we cannot add them. So the addition of two or more than two phasors is not possible in exponential as well as polar form. So what we need to do, we need to convert Z1 into rectangular form and Z2 into rectangular form. So we need to convert the polar or the exponential forms of Z1 and Z2 to rectangular form. So we consider Z1 and Z2 in rectangular form and we add them. So in rectangular form of representation, the real component of Z1 is represented by A1, the imaginary component of Z1 is represented by JB1. So Z1 is equal to A1 plus JB1. Z2 is in rectangular form. A2 is the real component of Z2 and B2 is the imaginary component of Z2. So we add these two phasors and the addition of these two phasors results in a new phasor quantity. So the addition of these two phasors which results in a new phasor quantity is equal to Z1 plus Z2. So we put the value of Z1. We know that Z1 is equal to A1 plus JB1 and Z2 is equal to A2 plus JB2. So the resultant phasor will be equal to A1 plus A2 plus JB1 plus B2. So here is the real component of the resultant phasor. The real component of the resultant phasor is A1 plus A2 and the imaginary component of the resultant phasor is B1 plus B2. So as we know, the real component of the resultant phasor as well as the imaginary component of the resultant phasor, we can convert this resultant phasor into polar form. If you guys want to convert this phasor from the rectangular form into polar form, you guys will have to calculate the magnitude of this phasor and you guys can calculate the magnitude. Why? Because the real component of this phasor is known and the imaginary component of this phasor is known. We know that under root square of the real component plus square of the imaginary component give you the magnitude of the phasor quantity. Similarly, we can find out the angle of the phasor, the resultant phasor. The angle will be equal to tangent inverse imaginary component by a real component. So we can find out, you see, we can find out the angle of this phasor quantity as well. So we can add two or more than two phasors in rectangular form. Let us talk about the subtraction of the phasors. So we talk about the subtraction of phasors and for the subtraction of phasors we consider two phasors Z1 and Z2. We consider them in exponential as well as polar form. So we want to subtract one phasor quantity from another phasor quantity, and for this mathematical operation we consider a phasor Z1 in rectangular form as well as polar form. So here is the magnitude of this phasor Z1. Here is the angle of this phasor Z1. If the phasor is in exponential form, we can easily convert it into polar form. Why? Because the magnitude of the phasor is known and the angle of the phasor is known. Similarly, we represent Z2 in exponential form as well as in polar form. Here is the magnitude of Z2, here is the angle of Z2. Similarly, here is the magnitude of Z2 and here is the angle of Z2. So let us subtract Z2 from Z1, and the subtraction of Z2 from Z1 results in a new phasor. So here is the resultant phasor, which is represented by Zs. So Zs will be equal to Z1 minus Z2, and let us put the values on the right hand side. So we consider these two phasors in exponential form. So we put the values. So the resultant phasor will be equal to the magnitude of Z1 into e raised to power j theta 1 minus the magnitude of Z2 into e raised to power j theta 2. So this will be the equation for the resultant phasor. And if this is the resultant phasor, then this resultant phasor will have a proper magnitude, which is represented by this symbol, and it will have a proper angle, which is represented by this symbol. So we cannot find out the magnitude of the resultant phasor from the right hand side. You see, you guys have the magnitude of Z1 on the right hand side, you guys have the magnitude of Z2 on the right hand side, but you guys don't have the magnitude of the resultant phasor. So we cannot find out the magnitude of the resultant phasor very easily from the right hand side of this particular equation. Similarly, we cannot find out the angle of the resultant phasor from the right hand side of this particular equation. If you focus on the right hand side of this particular equation, you have the angle of Z1, you have the angle of Z2, but you don't have the angle of the resultant phasor. So this is the problem with the exponential form. You guys cannot subtract one phasor from another one if these phasors are in exponential form. Similarly, we consider this mathematical operation in polar form. So in polar form of representation, the resultant phasor is equal to Z1 minus Z2, and we put the values on the right hand side of this equation. So we have the magnitude of Z1, we have the angle of Z1, we have the magnitude of Z2, we have the angle of Z2. So this is the equation for the resultant phasor. What is the problem with this equation? You see, if you focus on the right hand side, we cannot find out the magnitude of the resultant phasor, and we cannot find out the angle of the resultant phasor from the right hand side. If we consider the right hand side, we have the magnitude of Z1, we have the magnitude of Z2, but where is the magnitude of Zs? Where is the magnitude of the resultant phasor? How to find out the magnitude of the resultant phasor from the right hand side of this equation? This is a big question. Similarly, this resultant phasor will have a proper angle. So we don't know where is the angle of the resultant phasor on the right hand side. How to find out the angle of the resultant phasor from the right hand side? We can't do it. You see, you have the angle of Z1, you have the angle of Z2. Where is the angle of the resultant phasor? Nobody can answer. So we cannot subtract one phasor from another phasor if these phasors are either in exponential form of representation or polar form. So for this mathematical operation, you guys need to represent Z1 and Z2 in rectangular form. So we need to convert the phasors from polar form into rectangular form for the sake of addition as well as subtraction. So we consider Z1 in rectangular form. Here is the real component of Z1, here is the imaginary component of Z1. We consider Z2 in rectangular form. Here is the real component of Z2. Here is the imaginary component of Z2. So we subtract Z2 from Z1. So the resultant phasor will be equal to Z1 minus Z2, and we put the values of Z1 and Z2 in this particular equation. So Z1 is equal to A1 plus JB1 and Z2 is equal to A2 plus JB2. So the real component of the resultant phasor will be equal to A1 minus A2. Here is the real component of the resultant phasor, and the imaginary component of the resultant phasor will be equal to B1 minus B2. So here is the resultant phasor, and the resultant phasor is in the rectangular form. The real component of the resultant phasor is A1 minus A2, and the imaginary component of the resultant phasor is in and the result and the imaginary component of the resultant phasor is B1 minus B2. So the resultant phasor is in the rectangular form. We know its real component, we know its imaginary component. We can find out the magnitude of the resultant phasor with the help of its real and imaginary component. We know that under root square of the real component plus square of the imaginary component will give you the magnitude of this resultant phasor. We can find out the angle of the resultant phasor with the help of these two components. We know that tangent inverse, imaginary component by real component will give you the angle of this resultant phasor. So you guys will have to convert the phasors from exponential or polar form into rectangular form for the sake of addition as well as subtraction. We consider the multiplication of phasors, and for the multiplication of phasors we consider two phasors Z1 and Z2 in rectangular form. So let us consider these two phasors in rectangular form. Z1 is a phasor quantity and Z1 is in the rectangular form. The real component of Z1 is A1. The imaginary component of Z1 is B1. Z2 is another phasor quantity. The real component of this phasor is A2 and the imaginary component of this phasor is B2. We want to multiply these two phasors and the multiplication of these two phasors results in a new phasor. The new phasor quantity is represented by Zm. So Zm will be equal to Z1 into Z2, and we put the values of Z1 and Z2 on the right hand side. Z1 is equal to A1 JB1 and Z2 is equal to A2 plus JB2. We know that J square is equal to minus 1. This is Azan time, so let me pause this video. So we simplify the right hand side of Zm. So if we simplify the right hand side of Zm, we have A1 A2, we have J A1 B2, and we have J A2 B1, and then we have J square B1 B2, which is minus B1 B2. So if we simplify the right hand side of this equation, we get the real component of the resultant phasor, which is A1 A2 minus B1 B2, and we get the imaginary component of the resultant phasor, which is A1 B2 plus A2 B1, as the real as well as the imaginary component of the resultant phasor are known, we can find out the magnitude as well as the angle of the resultant phasor. So we obtained the real component of the resultant phasor and the imaginary component of the resultant phasor. So we can multiply two or more than two phasors in rectangular form. Let us consider the multiplication of these two phasors in exponential form. So we know that the multiplication of these two phasors result in a new phasor quantity, and we put the value of z1 and z2 in this equation. So here is the magnitude of z1 and here is the angle of z1, here is the magnitude of z2 and here is the angle of z2. So if we simplify the right hand side of equation number 2.57, we get the magnitude of z1 into the magnitude of z2 into e raised to power j theta 1 into e raised to power j theta 2. And the resultant phasor will be equal to z1, the magnitude of z1 into the magnitude of z2 into e raised to power j theta 1 plus theta 2. So this is the resultant phasor, and you see the resultant phasor has a proper magnitude as well as a proper angle. The magnitude of the resultant phasor is equal to the magnitude of z1 multiplied by the magnitude of z2, and the angle of the resultant phasor is theta 1 plus theta 2. So we conclude that if we want to multiply two or more than two phasors in exponential form, for the magnitude of the resultant phasors, we need to multiply the magnitude of the magnitudes of these phasors, and for the angle of the resultant phasors, we need to add these angles. So it's very easy to multiply the phasors in exponential form. Let us consider the multiplication in polar form. So we consider the multiplication of these two phasors in polar form. Here is the magnitude of z1, here is the magnitude of z2. So if we want to find out the magnitude of the resultant phasors, the magnitude of z1 multiplied by the magnitude of z2 will give you the magnitude of the resultant phasor, and theta 1 plus theta 2 will give you the angle of the resultant phasor. So the multiplication of the phasors quantity is very convenient in polar form. Why? We just multiply the magnitudes and we just add the angles, and this multiplication process becomes a very time consuming process if we have more than two phasors. So what we do, we consider the division of phasors. So let us consider two phasors z1 and z2 in rectangular form. So the division of one phasor quantity by another one results in a new phasor. We consider two phasors z1 and z2 in rectangular form. So let us consider z1 in rectangular form. z1 is equal to A1 plus JB1, Z2 is equal to A2 plus JB2, and let us divide Z1 by Z2. So this mathematical operation results in a new phasor. The resultant phasor is represented by ZD. So ZD is equal to Z1 plus Z2. We put the values in this particular equation. So we have A1 plus JB1 divided by A2 plus JB2. We are going to rationalize the right hand side. Why do we want to rationalize it? Because we want to find out the real component of the resultant phasor and the imaginary component of the resultant phasor. So in order to have the real component of the resultant phasor and the imaginary component of the resultant phasor, we multiply and divide the right hand side by the conjugate of Z2, and the conjugate of Z2 is A2 minus JB2. So we multiply and divide the right hand side of the resultant phasor by A2 minus JB2. So we multiply and divide the right hand side of the resultant phasor by A2 minus JB2. So we have A1 plus JB1 divided by A2 plus JB2 into A2 minus JB2 divided by A2 minus JB2. So let us simplify the numerator of the resultant phasor. So we multiply these two phasors quantities. So we will have A1, A2 plus B1, B2, and if we multiply these two phasors quantities, we obtain A2 square plus B2 square. Why? Because J square is equal to minus 1. So if we simplify this product, if we simplify the right hand side of this equation, we get A1, A2 plus B1, B2 divided by A2 square plus B2 square plus J A1, B2 minus A1, B2, A2, B1 minus A1, B2 divided by A2 square plus B2 square. So we obtain the real component of the resultant phasor and we obtained the imaginary component of the resultant phasor. So you know the real component as well as the imaginary component. You guys can compute the magnitude of the resultant phasor as well as the angle of the resultant phasor. Now let us consider the division of Z1 by Z2 in exponential form. So Z1 is in exponential form and Z2 is in exponential form as well. So we have the magnitude of Z1 divided by the magnitude of Z2, and we have e raised to power j theta 1, and if we take this quantity into the numerator, so we will get e raised to power minus j theta 2. So we have the magnitude of Z1 by the magnitude of Z2, e raised to power j theta 1 into e raised to power minus j theta 2. We simplify the right hand side of this equation, and the simplification results in the resultant phasor. So we have the magnitude of Z1 by the magnitude of Z2 into e raised to power j theta 1 minus theta 2. So if we look at the resultant phasor, here is the magnitude of the resultant phasor. So for the magnitude, we need to divide the magnitude of Z1 by the magnitude of Z2. Here is the angle of the resultant phasor, and for the angle of the resultant phasor, we need to subtract theta 2 from theta 1. So let us consider this division in polar form now. In polar form of representation, okay, let me consider it is in this division in polar. Let me consider the division in polar form. So ZD will be equal to the magnitude of Z1 and the angle of Z1 is theta 1 divided by the magnitude of Z2, and we have the angle of Z2, that is theta 2. So for the magnitude, we need to, for the magnitude of the resultant phasor, we need to consider this quantity, the magnitude of Z1 divided by the magnitude of Z2 will give you the magnitude of the resultant phasor. And for the angle of the resultant phasor, we need to shift theta 2 over here. So we need to change the sign of theta 2. It will become theta 1 minus theta 2. So the magnitude of the resultant phasor will be equal to the magnitude of Z1 divided by the magnitude of Z2, and the angle of the resultant phasor will be equal to theta 1 minus theta 2. So this is how we do the mathematical operations. This is enough for today. We will do the relevant numerical examples from my personal book in the second part of this lecture. Thank you so much.